Topics in the History of Mathematics. The Place of Music in Greek Mathematical Thought. A talk by Dr. Andrew Barker of the Department of Philosophy at the University of Warwick.
Most Greek thinkers refused to think of the world as an accidental jumble of bits and pieces. They conceived it rather as a coherent and orderly system, whose parts are related in the way they are because they are governed by intelligible principles of organization. The Greeks hunted for such principles, ones that would allow them to understand the perfect coherence of the whole, not only in the workings of the universe at large, but also in lesser systems, organisms, societies, even the human personality or soul. These too were conceived as displaying patterns of order and organized unity, like that of the cosmos itself. What kind of organization is it, then, that forges a genuine cooperating unity out of distinct and contrasting elements? What are the coordinating principles, and what is it about them that coordinates? The attempt to answer such questions dominated Greek approaches to a whole host of sciences, from cosmology and astronomy to political theory, biology, medicine, psychology, and many more. Two interlocking ideas are central to this tradition. First, that the principles of order in the universe are of a mathematical nature, and secondly, that they can be discovered through the mathematical study of forms of organization, order, and coherence that are most clearly represented in music, in the structures underlying melody. Not just any sequence of notes is a well-attuned scale, and a properly formed scale is a perfectly harmonious, well-coordinated unity forged out of diverse and contrasting elements. As Aristotle later put it, speaking of the doctrines of the Pythagoreans,
they supposed the elements of numbers to be the elements of all things, and the whole heaven to be a musical scale and a number.
The initial idea, then, is that the ordering of the universe and its subsystems is a harmonic ordering, and that the principles of harmonics, of musical attunement and organization are the question now is, what is a harmonic ordering, and what are the mathematical principles underlying it? Later Greek writers tell us that the first steps towards an answer to this question were taken by the great Pythagoras himself. Pythagoras was a real person. He lived in the latter part of the 6th century BC, but many legends accumulated around him, not all of which can be believed. Perhaps he really did make these discoveries himself. At any rate, what he is said to have found is this. Take a stretched string of any length you like and pluck it. A note sounds. Now stop it with a bridge halfway along. Pluck the half length, and the note it gives will be exactly an octave above the original. That is, it sounds like the same note, only higher, rather as if someone with a treble voice were repeating something sung by someone with a bass voice. The shorter length of string, remember, is half the length of the longer. Putting it in a slightly different way, the ratio of the longer to the shorter is 2 to 1. Next, go back to the original length and stop it 2/3 of the way along. The ratio of the original length to 2/3 of itself is 3 to 2, and the note from the 2/3 string will be at what we call the interval of a fifth, above the note from the whole string, in modern terms, for example, the interval from C up to G. Now, stop the original length 3/4 of the way along. the ratio of the whole to the 3/4 length is 4:3, and the new note will be at the interval we call a fourth above the original, for instance from C up to F. All these examples are good musical intervals, whereas if you stop the string just at random, you'll probably get musical nonsense. Similar results were found when other devices were used. Pipes of different lengths, vessels of different capacities, metal discs of different thickness, and so on. In every case, the musical intervals produced by sounding them corresponded regularly to the ratios of certain magnitudes involved in the sound's production. 2:1 gives an octave. 3:2 gives a fifth. 4:3 gives a fourth. I should perhaps explain that these terms, fifth and fourth, are nothing to do with the mathematics. They are used just because in the musical scale there are 4 notes in the fourth and 5 notes in the fifth. The neatness and consistency of the Pythagorean results suggested a further conclusion. In the case of the octave, for instance, the ratio 2:1 somehow expresses the relation between the notes themselves, not just that between 2 lengths of string. That is, one of the notes is itself, in some sense, twice the value of the other. What can this mean? The discoveries we have looked at seem to mean that notes have different pitches by differing in something like the way in which a big thing differs from a small one. They also show that the difference is not what we get by subtracting one quantity from the other, it is their ratio, which expresses how many times greater one is than the other. Twice as great, 1.5 times as great, and so on. But perhaps it seems odd to treat a note's pitch as though it were some amount of something or other. What are the numbers supposed to be numbers of? They started out, of course, as numbers of unit lengths measuring a string or a pipe. But obviously the pitch of a note is not the same thing as the length of a string or pipe that produces it. The most popular ancient solution to this problem is first found in the writings of the 4th century mathematician and philosopher Archytas of Tarentum, but it may very well be older. The idea was that a sound is a movement of the air, and that shorter strings or pipes, other things being equal, would move the air faster. Hence the higher note, the one produced by a shorter string, is a swifter movement. And what the numbers turn out actually to express is the relative speeds of movement of the sounds, the relative rates of their transmission through the air. Where 2 notes are an octave apart, for example, the higher moves twice as fast as the lower, hence the ratio 2:1. This physical theory is mistaken, of course, but the mathematics is none the worse for that. These points do something to explain why music formed part of the program of mathematical education called the quadrivium, which included arithmetic, geometry, astronomy, and music, or more properly, harmonics. It may help if you stop your cassette for a moment here and read through the discussion of harmonics in Plato's account of his own mathematical curriculum. This comes in Book 7 of the Republic, and you'll find it on page 72 in the source book. Let me draw your attention to just 2 things that Plato says. Here's the first.
I think that we may say that, just as our eyes are made for astronomy, so our ears are made for harmony, and that the 2 are, as the Pythagoreans say, sister sciences. Isn't that so?
This explains why harmonics comes into the quadrivium along with astronomy. Astronomy, on Plato's view of it, studies the relations between visible movements, ones that we can see occurring in space, in regular patterns but at different velocities and at different distances from us. Harmonics studies the relations between movements of another kind, ones that we cannot see but can hear. These relations can be described by a mathematics that deals with relative movement, when the notes are expressed by numbers representing velocities of movement, and when the intervals between notes are conceived as ratios between their velocities. Next, consider this sentence from the end of the passage. Plato is still talking about the Pythagoreans.
They do just what the astronomers do. They look for numerical relationships in audible concords, and never get as far as formulating problems and asking which numerical relations are concordant and why.
The reference to numbers and the question why are both crucial. Some relations between notes are concordant, musically proper, others are not. Now, relations between notes are mathematically expressible. They are ratios between numbers. But in that case, some ratios between numbers must be harmonious or concordant in a sense that mathematics ought to be able to explain. What is it about some ratios that makes the numbers related by them mathematically unified or well coordinated, while numbers standing in other sorts of ratio are not? We'll come back to this. But first, let's go back to an earlier stage of the tradition. We had reached a point at which the ratios corresponding to 3 sizes of interval had been identified. Notes standing in the ratio 2 to 1 are an octave apart. Those in the ratio 3 to 2 span a fifth. Those in the ratio 4 to 3 span a fourth. Now, these results are striking in their simplicity and neatness, especially because the octave, fifth and fourth are the 3 basic concords around which Greek musical practice and theoretical analysis revolved. Taken alone, of course, they amount to rather little, but they encourage the attempt to pursue such investigations further. By the time of Philolaus in the later 5th century, round about the time of Hippocrates, certain elementary calculations had been performed, taking these Pythagorean discoveries as their starting point. First, it was a well-known musical fact that the octave is the sum of a fourth and a fifth. That is, if you take some note as your starting point and go up a fourth, and then go up a further fifth, you will reach the octave above the original note. Now, the Pythagoreans could map this fact onto a statement about string lengths, that if you reduce a string's length by a quarter and the resulting length by a third, you reach the halfway point of the original length. Putting that quite generally, in terms of numbers, the ratio 4 to 3 combined with the ratio 3 to 2 gives 4 to 2, which is equivalent to 2 to 1. And this proposition could then be applied to sounds. If you take 3 quantities, in the case of notes, 3 speeds of movement, such that the biggest is related to the second as 4 is to 3, and the second is related to the smallest as 3 is to 2, then the biggest is related to the smallest as 2 is to 1. Secondly, the 2 basic subdivisions of the octave, the fifth and the fourth, are of different sizes, and the difference between them was itself an important musical interval. Take, for instance, the white note scale from E to E on a modern keyboard, which is almost exactly like one of the main Greek forms of scale. From E up to A is a fourth, and from E up to B is a fifth. Then the difference between the fourth and the fifth is the interval between A and B. It is called the tonos, or tone. Again, if you start from the top, from the higher E down to B is a fourth, and from E down to A is a fifth, which gives the same result. We can analyze the basic structure of the E to E octave as consisting of a fourth from E up to A, and another fourth from B up to the higher E. the 2/4 being separated by the tone A, B. Now, if the ratio of the 4th is 4:3, and that of the 5th is 3:2, and if this tone is the difference between them, its ratio turns out to be 9:8. You'll find this explained in your notes, and it was correctly computed at least by the time of Philolaus, if not before. Greeks working in music theory had learned, then, during the 5th century, both how to combine ratios, as when a 5th plus a 4th makes an octave, and how to take one from another, as when a 4th is taken from a 5th. Let us go on thinking about the octave that consists of 2/4, both of ratio 4:3, separated by a tone of ratio 9:8. The diatonic scale, on which most mathematical theory focused, breaks up these 2/4 into what we call tones and semitones. It moves through each 4th by steps of 1 semitone and 2 tones. Thus, in the white note scale up from E, the series E, F, G, A moves across a 4th by steps of semitone, tone, tone. And so does the series B, C, D, E. But when these steps are analysed mathematically, strange and disturbing results begin to emerge. Let me mention just one. Many theorists noticed that all the important musical intervals have ratios of the same sort. They all have the form n plus 1 to n. The Greeks called such ratios epimoric. Now, Archytas proved mathematically that intervals in epimoric ratios cannot be divided into equal parts. This seems very odd. By moving continuously through musical space, we can surely arrive at the midpoint of any interval. But if intervals are treated as ratios, we cannot. The proof is perfectly sound, and was probably as baffling to begin with as was the discovery that the diagonal of a square is incommensurable with its side. This result, and others like it, posed problems that urgently needed solving. Here is one that is crucial. The obvious way of dividing something systematically is to break it up into equal bits. But neither the octave nor any of its major parts could be divided into equal bits. So how could they be divided systematically? The general shape of the task faced by harmonics is summed up in the challenge issued by Plato in the Republic, which I mentioned earlier. Its main message is this, that the musical theorist's task is to find reasons, mathematical reasons, why a legitimate octave scale has the structure it does, and why other ways of arranging intervals inside the octave are unharmonious, not fitting together in a satisfactory way. What special mathematical property do the ratios of harmonic intervals have, which other ratios do not? The best answer proposed in this period introduces a new notion, that of mathematical proportion. Now, Archytas developed a classification of forms of proportion, which you will find set out on page 203 of the source book. He distinguishes geometric, arithmetic, and harmonic forms of proportion. And it is this classification that underlies a whole family of Greek divisions of the scale. Let me mention 2 examples. The first comes from Plato, in a passage which you'll find on page 79 of the source book. This part of the Timaeus is perhaps the most important single document in the history of the subject.
God did not, of course, contrive the soul later than the body, for when he put them together, he would never have allowed the older to be controlled by the younger. But God created the soul before the body, and gave it precedence both in time and value, and made it the dominating and controlling partner. And he composed it in the following way, and out of the following constituents. From the indivisible, eternally unchanging existence, and the divisible, changing existence of the physical world, he mixed a third kind of existence, intermediate between them.
Having thus made a single whole of these three, he went on to make appropriate subdivisions, each containing a mixture of same and different and existence. He began the division as follows. He first marked off a section of the whole, and then another twice the size of the first, next a third, half as much again as the second, and 3 times the first, a fourth, twice the size of the second, a fifth, 3 times the third.
You'll see that Plato is not discussing music as such, but the structure of what he calls the world soul, the animating and organizing core of the material universe. But his analysis treats this structure as a vast musical scale. And the point is that every note in this scale is located by the way it fits into the scheme of proportions that Archytas had set out. The notes forming the basic framework are all represented by numbers in a geometric progression, and all the others are inserted as means in either arithmetic or harmonic proportion between the terms of the basic series. The other example is provided by Archytas himself. His project was much more complex than Plato's, since he was trying to analyze all the scales of actual Greek musical practice, not just one. But through the apparent chaos of his lists of ratios, the same principle stands out. Every number in every one of his divisions is a mean in one or other form of proportion between other numbers in the series. Plato's challenge, you will remember, was to explain why a scale includes the ratios it does, and why they and not others make it a coordinated unity. We can now see what sort of an answer was being offered. It is not one that says the ratios must be of a certain special mathematical form. It says they are those ratios that divide the system and its parts in an orderly scheme of mathematical proportions. That is where the The mathematics of the subject became progressively more complex and sophisticated, not only in number theory, but also, and crucially, in geometry, where harmonic conceptions again played a major role. So too did the ways in which both harmonic arithmetic and harmonic geometry were applied to astronomy, as the intricacy of the planetary motions became gradually better known. But throughout antiquity, through the musicological theology of the Middle Ages, and right up to the time of Kepler and his astonishing essays on the harmonic geometry of the heavens, the original inspiration for the project continued to exercise a crucial influence on the development of its mathematics. The universe, however multifarious it appears, and however unrelated its parts may seem, is a single coordinated system, a divine harmony. Music, as we hear it, is a representation of that harmony. Its principles are mathematical, to be found in the study of ratios and proportions, and hence the mathematics of ratio and proportion must itself form an elegant, well-coordinated unity. To understand the propositions of this mathematics with all the complexities and difficulties that they involve is to grasp how they are all manifestations of a single universal principle of harmony, unity, and order